All right, this is the gas notes part 2. We pick up where we left off with Avogadro's hypothesis, where he said that equal volumes of gases at the same temperature and pressure contain the same number of molecules. So now let's take a look at these two balloons. We've got one on the left with hydrogen, one on the left with oxygen. The gases are at a pressure of 1 atmosphere and a temperature of 0 degrees Celsius. The balloon on the left contains 2.016 grams of hydrogen, and the balloon on the right contains some amount of oxygen. Now, we've got 3 questions. How many molecules of hydrogen are present in the leftmost balloon? And the answer is, well, you can tell because 2.06 grams is really 1 mole. And so if you have 1 mole, you have 6.02 times 10 to the 23rd molecules. So that's how much hydrogen is present. How many grams of oxygen are in the right balloon? Well, we know that they have the same volume and the same pressure and the same temperature, so they must also have the same number of moles. So if they have the same number of moles, that would be 32.00 grams, because that's the molar mass of oxygen. And what's the volume of each balloon in units of liters? If we use the ideal gas law, PV equals nRT, we're going to see we get 22.4 liters. And this is where the value comes from for the volume of 1 mole of an ideal gas. If you plug in the amount of 1 mole, 1 atmosphere, and 273 degrees Kelvin, you end up getting a volume of 22.4 liters. All right, so each gas sample has the same average kinetic energy because they're both at the same temperature. Are the molecules in each balloon traveling at the same average speed? If you agree, explain why. If you disagree, explain why not. Okay, the answer is no. And why is the answer no? Because molecules have the same average kinetic energy because they're at the same temperature, but they're not all at the same speed. If you've taken physics, you know that kinetic energy is 1/2 times the mass times the velocity squared. So if mass goes up, then velocity goes down, but not linearly. The lighter molecules move faster than slower ones. Now we want to look at each of these following situations and decide whether or not certain variables go up, go down, or remain the same. And we're going to assume that the amount of gas is constant. So we look at our first one in item J. A sample of gas is heated in a rigid container of constant volume. The pressure of the gas should go up. Why? Because we're heating it up. The gases are moving faster, more collisions with the container walls. The density of the gas should remain the same, however, because neither the mass nor the volume change, therefore the density doesn't change. The average distance between the gas particles should remain the same for the same reason. Density stays the same, so the distance between particles should remain the same. And the average speed of the gas particles should increase because the temperature or the kinetic energy has gone up. Okay? Now let's look at the next one, K. A sample of gas in a cylinder is fitted with a movable piston. The gas volume is reduced from 1 liter to 1/2 of a liter at constant temperature. The pressure of the gas should go up. I'm making the volume smaller, so the pressure should go up. The density of the gas should increase, and that's because the volume has decreased. The mass has stayed the same. The average distance between the gas particles should decrease because I've got the same amount of particles, but now they're in a smaller volume, so they're closer together. And the average speed of the gas particle should remain the same. Why? Because I'm at constant temperature. Hasn't changed anything. All right, item L. A sample of gas is in a rigid container of constant volume. Additional gas is injected into the container at constant temperature. So we would expect that the pressure of the gas should go up because I'm increasing the number of molecules that are inside the container. The density of the gas should also go up because I've increased the mass, even though the volume remains the same. The average distance between the gas particles should decrease, and that's because the density has gone up. I've increased the amount of mass in the container, so the particles are closer together. And the average speed of the gas particle should remain the same because I've done nothing to change the temperature. All right, section 10.4, the ideal gas equation. Everyone should know this. We write the ideal gas law with all capital letters except the number of moles. Traditionally, the number of moles is always written as a lowercase n. Everything else is uppercase. Now, let's talk about this gas constant R. If we use a value of 0.08206 for the gas constant, we have to make sure that pressure is in the units of atmosphere, volume is in liters, and temperature is in Kelvin. We're not required to use that one. That's the one that I have used the most often, but certainly you are not constrained to use that one. Feel free to use others. I think there are a couple of different values on the equation sheet that you'll get to use in May. If we use a value of 62.36, then the only units that change relative to the first part is the units for pressure, which now become torr or millimeters of mercury. And you can get that number by taking the value of 0.08206 and multiplying it by 760, and that value now that number becomes 62.36. Now we want to use this ideal gas law to calculate the pressure inside a helium tank that has a volume of 17.8 liters and contains 30 grams of helium at a temperature of 22 degrees C. All right, we can first compute the number of moles. We have 30 grams of helium divided by 4 grams per mole. That's 7.50 moles. The temperature is easy to get to. Just add 273 and we get 295 K. And now we rearrange the ideal gas equation to get P is equal to nRT divided by V. Plug everything in and we get 10 atmospheres. All right, question E. We want to use this combined gas law to solve the following problem. An inflated balloon has a volume of 30 liters at sea level and at 1 atmosphere. During its vertical ascent, the temperature changes from 25 degrees C to a chilly minus 19 degrees C, and the volume of the balloon increases to 55 liters. So what is the atmospheric pressure when the balloon has reached this higher altitude? All right, so we use our combined gas law, which says P1 V1 over T1 is equal to P2 V2 over T2. And by the way, we can derive all of Boyle's, Charles, and Gay-Lussac's laws, algebraic expressions of the laws, by holding one of the variables constant and seeing how everything else changes. But when we use the combined gas law, we want to solve for P2. So we rearrange this and we get P2 is equal to P1 times V1 over V2 times T2 over T1, and we plug in the things we know. 1 atmosphere, 30 liters for volume 1, and 273 minus 19 degrees Kelvin for T2, 55 liters for volume 2, and 273 plus 25 K for the initial temperature, and we get a final pressure of 0.46 atmospheres. Let me encourage you to stop the playback and do this computation for yourself. It seems trivial, it seems easy, and it is. But if you can't do this right off the top of your head, the problems on the exam are going to take longer than they should. So you need to practice this. We're going to get lots of practice in class. All right, section 10.5. further applications of the ideal gas equation. All right, so now let's talk about what happens with density. All right, so the density, in our case D, sometimes written as the Greek letter rho, of a gas is normally measured in units of grams per liter. So D is equal to mass divided by volume. Show how the density equation can be converted into this one. D is equal to MP divided by RT, where M is the molar mass. All right, so we know we have the ideal gas law, PV equals nRT, and we rearrange, or did we really just divide both sides by P and get V is equal to nRT over P. We know that density is mass divided by volume, and molar mass is equal, and we abbreviate molar mass with capital M. That's equal to mass divided by moles. So density then becomes N times M over nRT divided by P. All right, so if we look at this, we can cancel the values of N and move P up to the numerator, and we get M times P divided by RT. So what does this tell us? This says as temperature goes up, the density goes down. And we know that's true because we see this when we do heating of our homes in the wintertime. Let's look at problem B. The density of dry air at standard temperature and pressure is 1.29 grams per liter. What is the density of dry air at 100 degrees C, assuming that the pressure remains at 1 atmosphere? All right, that we assume 1 liter of volume. It doesn't really say that, but let's just make the math easy. Assume 1 liter of volume, and we use Charles' law to get the new volume. So 1 liter over 273 is equal to the second volume over 373, which would be the new temperature of 100 degrees Celsius. We solve for V2, we get 1.37 liters. Now we compute the density as mass divided by volume. We have our mass, 1.29 grams. We take our volume of 1.37 liters, and now we get 0.94 grams per liter. And then part C says, does this seem logical based on what you know about hot air balloons? And the answer is yes. Hot air, this new 100-degree air, is less dense. It's gone from 1.29 grams per liter down to 0.94 grams per liter. And so it's less dense, hot air rises. And that's what causes hot air balloons to go up. You heat the gas that's inside the balloon, its density goes down relative to the outside air, and so the balloon rises. All right, let's do a free response question, but I'm going to stop this now. I can't finish this before my 15-minute timer runs out. I'll stop this timer. We'll pick back up in part 3.